Chapter 3, Matter and Energy. So what exactly is matter? Well, matter has to have substance and it has to take up space. So we're looking at things that have mass and have volume, which means everything is made of matter. In terms of classifying matter, we can look at atoms or molecules. Atoms are the simplest form of matter. You cannot break it down any further. So it is effectively the smallest particle of matter. A molecule is when you take two or more atoms and join them together. So it is more complex than an atom, which means that you can break a molecule back down into its individual components or its individual atoms. Some matter exists purely in its elemental form, so only one type of atom. Some elements exist as molecules, which it's still the same type of atoms, but things like oxygen, O2, you have two oxygen atoms bonded together, that's considered a molecule, but you'll never find oxygen all alone by itself in nature. So the three typical states of matter that we're going to talk about are gases, liquids, and solids. And how do these differ from each other? So a gas is going to be the state of matter where the particles are farthest away from each other, they are moving the fastest, they can be compressed, which means you can fit the molecules or atoms into a smaller space. And typically you're going to see a very low density, right? So mass per volume. In a liquid, we have molecules or atoms that are still able to move around, but they're not moving as fast as a gas. So they're able to slide over each other. Liquids can be slightly compressed. For example, brake fluid can be compressed to a minimum amount, but typically you cannot compress a liquid. In terms of a solid, the least amount of flexibility in terms of how much the atoms or molecules can move. So they're packed as closely as they can be, which means that you cannot compress a solid anymore. A couple other things that we can look at is volume and shape of the three types of matter. So we see here, as I discussed, in a solid, how close the particles are. In a liquid, they're a little bit farther apart, which means they can have some freedom of movement. And in a gas, they're really far apart. We can see that they're moving around here. In terms of volume and shape, the volume and the shape of a solid is definite. So it is what it is. It doesn't matter what type of container you put it into, it still retains its shape and its volume. In a liquid will always have a definite volume. However, it has an indefinite shape. So that means that if you pour it into different containers, it will take on the shape of the container itself. But it does not change its volume. In terms of gases, this is where we see a substance that has an indefinite shape and an indefinite volume. So neither of those things are fixed, which means that transferring a gas from one container to another, the gas takes on the shape of the container as well as the entire volume of the container. So these are some other ways that solids, liquids, and gases differentiate from each other. So how can we break down matter into classifications? Well, with matter, we're either looking at a pure substance or a mixture. And a pure substance means that you only have one type of substance there. A mixture means you have more than one type of thing, right? We mix things together versus something that is pure. We can further break down a pure substance into an element or a compound. So an element is going to mean that you only have one type of atom present. For example, sodium, hydrogen, iron, tin, mercury. That's it. That's all you see, just one element. Only one type of atom is present if we're looking at an element. In a compound, that means that we have two different types of elements bonded together. So an example would be salt, which is sodium chloride, NaCl. Water is a compound, H2O. So in both of those examples, you have two different elements that have come together, formed a bond, and now we say that is a compound. If we break a mixture down, we can either say that it is homogeneous or heterogeneous. Homogeneous meaning it's the same throughout, heterogeneous meaning it's different. So once again, a mixture is either some elements and some compounds together or two different compounds or whatever, but we don't have just one thing present. So if it's a homogeneous mixture, as I said, that means that it's the same throughout. So when looking at that, you want to ask yourself, if I pull a little piece of this out, if I take a sample out of this, is it going to look or have the same composition as what I took it from? So does the sample look like the whole substance, the whole thing that I have? If so, then it's homogeneous. If what I take out is different, if it looks different than what I got it from, then we say that it's heterogeneous. So air, right? Air is a homogeneous mixture because there's not just some oxygen in a little pocket and some nitrogen in a little pocket and some CO2 somewhere else. No, they're all mixed together, evenly distributed throughout a space. A heterogeneous would be oil and water or salt and pepper. So if you mixed your salt and pepper together, would you truly get, 10 grains of salt and 10 grains of pepper in each sample? No, probably not. So how can we classify matter then? Let's take a look at some examples. Chlorine. Well, chlorine is an element, so then we would say that is a pure substance. Water is a compound. It is a pure substance because water is water. It's always H2O. Soil. Think about all the different things that you can find in a sample of soil. We would consider this to be a mixture, and it is heterogeneous. Salt water. Well, we've taken salt, which is a compound, and we've mixed it with water, which is a compound. So we have a mixture. Now the question would be, where did we get this salt water from? Did we simply throw some salt in our pot because we wanted to boil some water to make spaghetti? Or is it salt water from the ocean? If it's salt water from the ocean, it's going to be heterogeneous. If it was salt that you added to your tap water, it's going to be homogeneous. Oxygen. Oxygen is an element, so it is a pure substance. Carbon dioxide. That means there's one carbon atom bonded to two oxygens. So since I have two elements that have come together, that is a compound, but it's just one compound, so it is a pure substance. Rocky Road ice cream. That is a heterogeneous mixture because you have all those chunks of chocolate and marshmallows and whatever else is in there, right? And each bite is different from another bite. Alcohol. So there's different types of alcohol, but alcohol is a compound. It is bonds between carbon, hydrogen, and oxygen. So we would consider that to be a pure substance, unless we're talking about like a mixed drink or something that has some ice in it, and now we have a heterogeneous mixture. Air. We talked about air. The air is a mixture of nitrogen, oxygen, carbon dioxide, some other random things floating around. But air is consistent throughout, so we say that it is a homogeneous mixture. Cement. So cement is what we mix together to make some concrete, and that in and of itself, all those little particles are not going to be of the same size and consistency, so we would say it's a heterogeneous mixture. So we've looked at the ways to identify or classify our matter, right? And in looking at whether it's a pure substance or a mixture, it can be in a solid, liquid, or gaseous state. So now what happens if we wanted to maybe separate out some of those things from each other if they're a mixture? Or we wanted to just simply analyze what we have present. So we can look at both the physical properties and the chemical properties of our substances. So your physical property is something that as you are observing it, it is not changing what you have present. So typically these things are what we can observe with our five senses. What color is the solid or liquid? Does it smell bad? If it's a solid, is it really hard or is it a soft metal? These are different things that we would consider to be physical properties, along with, say, boiling points, melting points, sublimation points, so temperatures that would be associated with when a substance changes from one state of matter to another. In a chemical property, what you are observing is going to change that substance. So that's the big difference between physical and chemical properties. Is a physical property, or what you're observing is not changing the substance, while a chemical property would be changing it. So is a substance flammable? Does it react with an acid or a base? Does it oxidize metals? Things like that would be chemical properties. So then we can look at a physical change versus a chemical change. And when we're looking at changes, right, this implies some sort of action, which is different than a property. A property is more like an observation, while a change is an action. So a physical change is going to be one that is easily reversed. I can dissolve salt into water, and then if I boil the water, I can get the salt back out. And I have not changed the water nor the salt. So most physical changes are looking at changes of state, going from a gas to a solid, or a liquid to a solid, or a solid to a gas. So changes in states of matter are always going to be physical changes. Your chemical change is looking at a rearrangement of the atoms that you start with. So you're going to be making bonds because you broke some bonds. So you're actually changing what you have there. It is basically a chemical reaction. So as I was just saying, your chemical changes are looking at chemical reactions. And this involves breaking bonds and making new bonds. In a chemical reaction, we're still going to obey the law of conservation of mass. And we can identify in a written equation what's happening. So on the left side, we're going to see our reactants. So in this reaction down here, it's saying hydrogen is going to react with oxygen to form water. And we'll talk later about what these numbers in the front mean, but that's why, or this is how we observe the law of conservation of mass, by putting these, what we call coefficients, in the front. So reactants are always to the left of the arrow, products are always on the right, because this is what's coming together to produce, right? The arrow is showing we're producing this over here, so your product always sits over here. And as I said, we always have to obey the law of conservation of mass. And this also means that if we start with hydrogen, we end with hydrogen. We're not doing nuclear reactions where we could change hydrogen into helium. So in all chemical reactions, all of the elements that you start with, you have to end with the same number and types of elements. They can just be bonded in different ways. And this particular reaction here is considered a combustion reaction because of the oxygen that is reacting. So this shows an example of how we can separate things by physical properties. So this would be a physical change. So here we have a watch glass filled with some iron filings and some sand. Well, iron is magnetic, sand is not. So if we bring a magnet over, that means that we can separate out the iron from the sand. So we're changing a mixture back into some pure substances, right? Sand all by itself is a pure substance, and iron all by itself would be a pure substance. So some examples of matter and their properties. How would we identify these things? Color. Well, color is something I can just observe with my eyes, and by observing it, I'm not changing the color of it, so color is a physical property. Flammability. Well, this is saying whether something is going to burn up in flames or not. Once you ignite it on fire, it's not going to be the same once it's done. So flammability is a chemical property. Hardness. I can touch a piece of metal or a crystal and see, is it really hard? Is it really soft? That is a physical property. Odor is a physical property. Some chemicals smell pleasant, others do not. Oxidizer. So this is saying whether or not something will oxidize. That implies that it can undergo a chemical reaction. So whether something is an oxidizer or a reducing agent, anything like that, that is always going to be a chemical property. And how about looking at some changes? So when boiling water becomes steam, we're not changing the water, we're just changing the state. If it's boiling, we're talking about that it's in a liquid and it's becoming steam, so it's becoming a gas. That is a physical change because we're changing states of matter. Butter turns rancid. Can we get the butter back before it turned bad, right? No, we can't. Once it turns sour, that's the end game, right? So that is a chemical change. That's a chemical process. Burning wood in the fireplace. Once again, once we've burned the wood, it turns to ash, and you cannot turn that ash back into wood. Therefore, that is a chemical change. If a mountain snowpack is melting, well, if it's snow, it's going to be solid. If it's melting, it means it's going to become a liquid. So going from a solid to a liquid is a physical change. Decaying of leaves in winter. So the leaves fall off the tree, they start to decompose. We don't get the leaves back. The ground doesn't suddenly sprout the leaves back up. Now we know the tree can grow more leaves, but once those leaves decompose, that's it. We can't change it back. That's a chemical change. Dissolving salt into water. That is a physical change because there is a way that we can physically separate the salt away from the water if we chose to do so. So things like solubility, if something dissolves in something else, solubility would be considered the physical property, and then separating it back out would be a physical change. So this chapter was about matter and energy, so let's talk about energy. So energy is the capacity to do work. And the units for that are joules, kilojoules, calories, kilocalories, kilowatts. So these are units for energy, but it's all about this is available. It's the capacity to do work. So what's work? Well, work is applying a force through a distance. We can look at different types of energy. Our two main types of energy are kinetic and potential. Kinetic energy is the energy of motion. So two different types of kinetic energy are thermal energy and electrical energy. Thermal energy is the energy of particle motion in a particular substance. And the more thermal energy a substance has, the higher the temperature. Electrical energy is the movement of electrons from one place to another. So electrons are moving, that means it's kinetic energy. And anytime we're talking about things that are moving, we're talking about kinetic energy. So your potential energy is stored energy or energy of position. The best example in chemistry is chemical energy. Where are we storing energy? We are storing energy in bonds. Right? So when you eat and your body's digesting and making that energy, it's coming from the fact that it's breaking bonds in the food that we eat and then turning it into a different form of energy that our cells can use. So chemical energy is energy stored in bonds. Evaluating changes in energy. So we want to look at the system versus the surroundings. So the system is going to be what is it that we're studying? What is it that we're interested in? Versus the surroundings, which is everything else. So we can have two different situations where either heat is coming into the system or heat is leaving the system. Just like in the law of conservation of mass, we have a law of conservation of energy, which says that energy must be conserved. We cannot create it or destroy it. We can change it from one form to another. We can change chemical energy into electrical energy and vice versa, right? We can turn solar energy into electrical energy. So where's all this energy coming from? Well, it's coming from all of these different atoms coming together, making bonds, breaking bonds. And we can also simply look at Einstein's favorite equation, or famous equation, I should say, E equals mc squared. So that means that we can take energy and turn it into mass. We can take mass and turn it into energy. So these things are continually happening. E equals mc squared has to do with nuclear chemistry. But in terms of what might be most common for us is heat, a transfer of heat. So heat is a transfer of thermal energy. When you put a hot object in contact with a cool object, the heat will transfer always in the direction of hot object to cool object. So we have our kinetic energy that we can look at with heat. We can look at our potential energy, which has to do with bond breaking and bond making. So 2 types of reactions. We either have exothermic or endothermic. And in exothermic reaction, we're always looking at there is a certain amount of energy that is being released. That energy that is being released can then be harnessed to do work. So what does this mean? The energy that's required to do the reaction is less than the energy that is given off. Where does the energy come from again? Well, we put in energy to break bonds. Then we release energy or give that energy off when we make the bonds. So that means we had to put in less over here and we got more out over here if it's exothermic. We can also think of it as if the energy is exiting. So exothermic is exiting energy. And in terms of signs, mathematical signs, we would always assign exothermic energy as being negative because the system is losing that energy. So then just the opposite, we have endothermic reactions. So now what it is we have to put in more energy than the energy we get out. If we think about it in terms of riding a bicycle up a hill, if the hill that we're going up is really, really tall, but the hill that we're going down is really, really small, well, we don't get to have as much fun, right, on the downside slope. So energy is coming into the system. Endo means energy is coming in. That energy would be considered to be positive. So looking at breaking and making bonds, we have to put in more energy to break the bonds than the energy that gets released when we make the bonds. Now, regardless of whether a reaction is exothermic or endothermic, energy is always required to break bonds, and energy will always be released in making bonds. So we can look at what we call potential energy diagrams. And enthalpy is just a fancy word for saying energy transfer or heat associated with a reaction. So when we start up a really high energy and we end at a really low energy, that means that there was a certain amount of energy given off, right? The hill, we can look at this as a hill. When we get to go down a big hill, we get to have a lot of fun and a lot of energy comes off. Versus if we start off at a really low energy, but we end at a higher energy, well, we had to put all this energy to get into the top of the hill, and then what? No fun. So this is the energy you have to put in. That is an endothermic, right? This is the energy that gets to be released. So this is exothermic. Typical type of exothermic reaction is combustion. So when we burn methane, we get some carbon dioxide and water, and we get the energy coming off as a product. An endothermic reaction, example down here, is decomposition. So we're breaking down ammonia back into its elements. And we see here that the energy is a reactant, which means it is required to get the reaction to go. So there are 3 different types of temperature scales that we're going to look at. The first and most important one is Kelvin. And notice that this is different because we don't say degrees Kelvin like we do with degrees Celsius and degrees Fahrenheit. Who discovered this? William Thomson, aka Lord Kelvin. He studied gases, the effects of temperature, pressure, and volume. And what he saw was that no matter what type of gas you had, the volume in relationship to the temperature would always extrapolate back to a certain value. So whatever the pressure of the gas was, didn't really matter. In studying the volume temperature relationship, right, the volume would shrink the cooler the gas would get. All gases behave this way. So this property in terms of temperature, with what Lord Kelvin did, it wasn't simply one substance. It held true for all substances. So your Kelvin is what we call our absolute temperature scale, which is why it doesn't get degrees with it. Now, both degrees Celsius and degrees Fahrenheit were based off of the properties of water. And so at what temperature does water boil? At what temperature does water freeze? that is how these two temperature scales were determined. So you could make up your own temperature scale based on another substance and determine what temperature it boils and it freezes, and then you create a temperature scale. So over here are some common temperatures. We boil water at 100 degrees Celsius. Body temperature is around 37 degrees Celsius. Room temperature is about 25 degrees Celsius. And freezing point is 0 degrees Celsius. Kelvin and Celsius temperature both change in the same amount. So every increase or decrease in degrees Celsius is equivalent to an increase or decrease in Kelvin. Not true for the relationship between Celsius and Fahrenheit. But here we have our equations in terms of how can we convert from one temperature to another. So when you're looking to solve for these, what you want to find will be all by itself, and what you are given will be on this side of the equation. So if I'm asked to find degrees Celsius because I was given degrees Fahrenheit, I would use this equation. If I want to find degrees Fahrenheit because I was given degrees Celsius, I use this equation. If I want to find Kelvin, I have degrees Celsius, I use this equation. Now, there is no direct conversion between degrees Fahrenheit and Kelvin, so it would be a two-step process. And let's look at that. So normal human body temperature can range between about 36 degrees Celsius and 37 degrees Celsius. How can we express these two temperatures in Kelvin? So we use is given and 37 degrees is given. So we simply plug it into our equation, we add, and see then that the temperature scale or temperature was 310 Kelvin to 309 Kelvin. Body temperature that is above 39 degrees Celsius, we consider that to be a fever. How can we convert this into the Fahrenheit scale? Because if we came to work or to school and said, oh, my temperature is 39 degrees Celsius, people might be like, oh, wow, that's really low. So we're going to use degrees Fahrenheit because we were given degrees Celsius. So we plug our 39 in here. Order of operations says we go 39 times 1.8, and then we add in the 32. So sure enough, that would give us a temperature of 102 degrees Fahrenheit, which is considered to be a fever. A couple more things to do with energy. So we can talk about specific heat capacities. And I have some listed over here. So the specific heat is looking at how much energy do you have to put in to change the temperature of 1 gram of a substance by 1 degree Celsius. So that means here's our units, joules per gram degree Celsius. So these units are on the bottom multiplied together. Your heat capacity is simply how much energy it takes to change a substance by 1 degree Celsius. So we're taking out the mass and just looking at joules per degree Celsius. And you would not think so, but there is a possibility where you can have a bathtub full of ice water that would have more heat capacity than a small warm cup of water. Why? Because of the temperature that things are at and actually the quantity that we have. So we can use specific heats to look at calculating heat that is either absorbed or released in a particular reaction. So we have Q, which is heat, and that would have units of joules. Your M stands for mass. The units have to be grams. Your specific heat is in units of joules per gram degree Celsius. And your delta T is a change in temperature, and that has to be measured in degrees Celsius. When we look at a change in temperature, anytime you see a delta in the front, it's always going to be the final state minus the initial state. So final temperature minus initial temperature. And just looking at some of these specific heat capacities, and we always want to ask ourselves, oh, well, why do we care, right? So let's say, I've seen commercials for the copper skillet or the copper pan, and then we know we can use a cast iron skillet to heat things up. So in comparing the specific heats between copper and iron, what does this mean? Well, if I have two pans and they weigh the same amount, I'm going to have to, and I apply the same amount of energy, I can get my copper pan to heat up faster than my iron pan, right? Because this is a lower specific heat. So I can change the temperature more based on the energy that's given. But what do I also know? If I turn off the heat source, it's going to take longer for the iron to cool down because it has a higher specific heat. So that's why specific heats can be of value. Now looking here, our typical solids and metals have lower specific heats than, say, water or ethanol. So water has one of the highest specific heats. This is really important because what this means is for big bodies of water, you can get a layer of ice that forms on the top, but the water underneath is going to stay, I mean, it's going to get cooler, but it's not going to freeze, right? So that means that your aquatic life, plants, etc., aren't going to die off every winter. So how can we use our equation? Calculate the heat required to heat 1.01 kilograms of water from 0.05 degrees Celsius to 35.81 degrees Celsius. So what's the equation that we're going to use? Well, it says calculate the heat. So I need to have heat. I'm given something in units of kilograms, which means that's a mass. And I have two temperatures. So that means I have mass, I have heat, I have temperature, which leads me to our heat equation. Couple things, right? We always are just identifying our given information. So we list things, 1.01 kilograms. The specific heat of water is 4.184 joules per gram. That should say degrees Celsius. That's an error on my part. Our initial temperature and our final temperature. In reading this, I look for clue words. It says from 0.05 1. So if I'm from and to, I'm going from the store to my house. My initial state was the store. My final state was my house. So from is going to always be initial. To is going to be your final. Now, in looking at this, my units here are grams. My units here are kilograms. I cannot directly multiply these together because my units wouldn't cancel out. So I'm going to have to convert my kilograms into grams and then perform the rest of the calculation as written. So plugging in my mass, 1.01 kilograms, doing the conversion to get it into grams, multiplied by C, my specific heat, times my temperature change, which is final temperature minus initial temperature. And I see all of the units that cancel out. I'm left with units of joules, which is important because that is the unit for heat. If I ended up with something else, some other unit, then I knew that I did some math incorrectly. So in looking at this, how do we know how many sig-sigs that we want to use, right? We go back to our initial values and pay attention to those rules. So 151,000 joules is 151 kilojoules.